Hello viewers and welcome to another episode of Space Science with Python. Today we will not cover the Earth again, don't worry. I think we had a nice first deep dive into space and the Earth. No, today we will talk about our center or the center of our solar system. Now, maybe you recall that our computations have been performed with respect to the Sun. So we computed the state vector from the Sun, or as seen from the Sun of our home planet, from the center of the Sun. And you know, well, based on Kepler's law, this is also true. The center of the solar system, or not the center, but the planets revolve around the Sun, either on a circle or an ellipsoid, where the Sun is in one of the focal points. And today we will cover the topic whether this is 100% sure or not, because the Jupiter, Saturn, the Earth, all planets basically, all asteroids, they have also their own mass and they contribute something with the gravitational pull. So it's not entirely the Sun in the center, but more like a mixture, a superposition of all the gravitational influences in our solar system. And today we will have a look whether the planets that are compared to the Sun rather small have any significant effect or not. Now, for this, we will compute the difference between the center of the Sun and the Solar System Barycenter. So the Solar System Barycenter has a different ID in the SPICE framework than the Sun. Now for today's session, we have a new folder, which is called the SSB, so the Solar System Barycenter. And I also prepared something. I prepared some new kernels. So we have a new kernel which is here in PCK called PCK00010PPC. We'll get back to this later, why I need this. And I didn't want to dive into the repository and show you where it is. It's just now gathering everything here in our project folder, which is growing and growing. And we have in our SSB folder, already the prepared Jupyter notebook, but also another text file called meta or kernel meta.txt. What do we have here? Well, it's a format provided by SPICE. Instead of loading all the kernels individually, like the SBK, LSK, and so on, we can put everything in this meta file in this structure after begin data. And this data is then loaded by the SPICE kernels in the Python function. So now we have only 3 kernels. You may think, well, a little bit overkill, but for example, if you use the spacecraft missions, I don't know, Cassini or whatsoever, you can have 20, 30, or 40 kernels, and then it's a little bit overwhelming to add all these files or file names into your script. So that's basically the setup. I also created or rebuilt. No, I didn't. I rebuilt the container because I added also matplotlib this time. And let's see how we proceed. Now our VS Code environment, everything is running. Our container is running and everything. So we have our working environment. If you don't know how to do it using remote containers, just recall the second video, setting everything up with remote containers. The link is also in the description. Now again, before we start coding and hacking, what do we want to do? We want to see whether there is a difference between the center of the Sun and the Solar System Barycenter. So we want to compute the distance between both. And we also assume, because the planets are revolving around the Sun, that this is also time dependent. And well, some planets take years or decades to revolve around the Sun, so let's cover a large period of time. So we need something for the time, we need SPICE, and also let's work with NumPy since we want to compute some distances and we can use the nice NumPy functionalities. So let's start by importing some basic libraries. And of course, later for plotting, we need also matplotlib, but let's import it later. Now you see we can now load the kernel file, the kernel meta.txt, that is in the same directory as our Jupyter notebook. So we can just execute it and it's running. Nice. Again, comments and everything will be added later. So just take a look at in the repository. The link is also in the description if you want to go everything step by step, and also if you want to understand it more deeply and not only here in this video. Yeah. Now we want to have some kind of, let's say, call it initial time in UTC. So some starting period where we want to compute the difference between or the distance between the Solar System Barycenter and the Sun. Let's take the year 2000 and yeah, let's say the first month and also the first day, so the 1st January. And we take the hour, yeah, let's take it midnight. So we just keep it very simple. And we will not compute it now for every second, but let's say, well, maybe in days. So let's say we want to have some delta days, and how many days? Let's take 10,000 days. So we will compute 10,000 data points, 10,000 days. Just quick recap. I mean, every year has 365 days. So this should cover something like, I don't know, like 30 years or something. Okay, now we can, yeah, we should also convert this later to a format that SPICE can use, but let's first compute also the end time of our computation, and this is basically our initial time in UTC plus the date time delta, and there we say the number of days is delta days. So yeah, you can just play around with the delta days if you want to see a difference, or if you want to extend everything. Feel free to change values and see how this value behaves over time. Now for SPICE, we need also yeah, to convert it into a proper string format, because now we have a date time object. So let's do it here. First, let's execute it and check whether everything works. Looks nice, perfect. Now we use this initial time UTC and we want to have it as a string. And there we use, yeah, the initial time UTC and then as last time strf time, where we convert it into a format that SPICE can work with it or knows the format. So it's %d, and then we have t. What was, yeah, it was hours. So hours a huge H, capital H. Then we have, I think, minutes, and then seconds. I confused myself a little bit. Let's take a look whether this makes sense or not. No, I did a mistake here. Yeah, this is live programming without any support. Ah, yeah, there it is. Okay, this looks nice. And we can basically apply the same method for the end date. Well, not like this, but in another line where we just say, okay, let's take the end date and the end. So this should be working. And I didn't run it now. Yeah, and you see it's almost 30 years. So from the year 2000 to 2027, our calculation will cover this time period. Cool. Now we can convert it into our SPICE format. So yeah, let's make some copy paste. We say the initial time in ET, so the ephemeris time is spicy pi no, this is wrong, UTC to ET, and then paste the string. And the same applies also now for the end date, where we put this here, and here we write end time ET. And it ran also through. Perfect. Let's verify. Yep, that looks good. Now, we want to compute the difference or the distance between the Solar System Barycenter and the Sun, or vice versa, doesn't matter. So let's store everything. So the Solar System Barycenter with respect to the sun, but the position. So not the state vector, but only the position will be stored in a list. And let's also convert, or create, not convert, but create an array that contains the ephemeris time, the initial ephemeris time, and the ending, or the end of the calculation in 10,000 steps. So we use NP linspace. So we create an array starting from the initial time in ET to the end time in ephemeris time. And the delta, so the steps are delta days. So this should give us an array with 10,000 entries from the initial time to the end time. Now let's verify this. Yeah, okay, we have a lot of values here. And now what is the length? 10,000 as expected. Nice. Now we can iterate through this array, and for each time step, so each entry in the array is a time step, we can compute the position vector between the sun and the Solar System Barycenter, and we append it in our array. I know more advanced people will now say, don't do a for loop, do it in a list comprehension. You can already apply also the what is it name? The distance, the Euclidean distance, everything. Yeah, but let's keep it a little bit clear for those of us who are not yet very familiar also maybe with Python. I know this is not really a Python introduction video, but maybe some of you are just starting or beginners. So let's start with more familiar concepts. So we want to iterate through our array, and we use the same name basically, but only with an F. So yeah, and now we use a temporary value. We say it's position, and the second output is a light time, but we don't need it. And what we do is we use SPK GPS. So GPS is like geo, but the difference is that it's it does not return our velocity, but it returns only the position of our values. So the target is 0. It's the Solar System Barycenter. The ET is the time interval from our step in the for loop. We have our reference frame. Let's use also again ecliptic J2000. And we have our observer, and this is the sun. So we don't get a state vector, only the position. And now the result can be simply appended to our already created empty list. Yeah, and then finally we can also convert this into a NumPy array. Now let's see whether this works. Yeah, it ran quite quickly through. Perfect. And now we can compute the position, or not only the position, but also the norm later of our Solar System Barycenter position vector. We can do either now normalizing it, or we use later maybe a 3D plot. So let's stick maybe with the position. But the values now, they are given in kilometers, so it's probably quite confusing to work with these values. We want to compare it with the sun. So what could we do? We could normalize it with the radius of the sun. So this would help us also creating a way easier, more understandable plot. Now we want to compute the radii of the sun. Why the radial? Well, recall the function from last time, this bot VCD, and where we can extract parameters from any body. And the sun parameters are now in this PCK kernel I just added in the repository. And the number of radii that are extracted, we get 3 radii for the X and Y direction and for the Z direction. So basically the sun is not a sphere, but more like an ellipsoid, because due to the rotation of the sun, the radii in x and y direction are a little bit larger than to the z direction, but we just use the x direction. This is fine. So we want to extract values from the body ID 10, which is the sun. What kind of items do we want to extract? We want to extract radii, and how many values do we expect? Well, we expect 3 values. Now we can compute this and just quick look the radii of the sun. Yeah, we got 3 results, and well, I said it, but probably Spice didn't include it. All values have the same result, so a little bit embarrassing for me now, but the radius into z direction should be a little bit smaller though. Well, anyway, let's stick with this. So we say the radius of the sun is equal to the radius of the sun, only the very first entry. I think this is fine. Oh, and now we can normalize our our vector from the sun to the solar system barycenter. We can just call it scaled or normed and divide it by the radius of the sun. Now let's have a look here. How does it look like now? And yeah, we have now other results. Now, before we go into the results, well, creating a picture would be more helpful, right? So let's make a plot with matplotlib. And what do we want to achieve? We want to, let's make a simple 2D plot. We want to just get a view from the top. So just the X and Y direction should be sufficient. So let's extract it here. We call it now this, and then XY, and take the vector and only take everything, but only from the first and the second column. And now we can create the plot. Well, first of all, space is dark, and we love dark mode also. So let's use the dark background. So that everything is pitch black. Now we can create a subplot with figure x equal to plt subplots. No, it's not auto-completing. I didn't import it yet. Subplots, figure size. Let's take my absolute all-time average default, either 10.8 or 12.8, maybe 12.8. Invalid syntax. Okay, as PLT, just making it, running it from time to time. Okay, now this is how the plot looks like. Now we can create the sun first. We normalized everything, so the x and y direction is not kilometers or AU, it's the number of radii, sun radii. So the sun should be here a unit sphere or unit circle. So we can simply create the sun by saying, okay, let's take the circle, we put it into the center. I know it's not the center of the solar system, but we use it as a reference, so we want to compare it. And then we can say, okay, the radius is 1.0 because we normalize with respect to the sun. The sun is yellow, I would say. And I didn't add it yet to the plot. So x at artist sun circ. Wow, okay, my eyes are burning. This is not good. Let's make an alpha or something. Yeah, 0.8 or 0.6. Yeah, this looks a little more humane. And we only cover a quarter of the sun, so we should also set some limits here as well to see the entire sun. So the x limit goes from, I don't know, -2 sun radii to +2 sun radii. And the same applies also for the y lim. Yeah, like this. And it's a little bit, looks a little bit like an egg. Maybe also because, yeah, the figure size, I mean, it's my default, but yeah, we should have it equal, aspect equal. I think there's also a command there. I think set aspect ratio or something. Aspect ratio? No? Aspect, yeah, aspect, and this is then equal Yeah, okay, so I don't need then the figure size is normalized. So this is the sun. It goes from 0 to 1 sun radius into each direction. It's not really surprising here. Now, what else can we add? We can also add a grid maybe for later for the human eye to make it more easier for us. So we can say line style is equal to dashed, and also let's take a look, and also reduce maybe the alpha value a little bit. I don't know, 0.5. Whoa, what did I do? Oh no, I just created a new cell. Okay, everything is fine. No reason to shut down the video. Okay, cool. Now we have our X and Y direction. We should maybe also add some physical parameters. I mean, a lot of people don't do this, you know, like saying, yeah, it's self-explanatory, but yeah, let's do it here. X in sun radii, I would say, or yeah, radii. And the same thing applies for the Y direction as well. So we have something that looks decent. Yeah, but where is, okay, the Y. And there we go. So this is now something we can work with. Now we need to add also the sun, the distance between the position of the solar system barycenter with respect to the center of the sun. Now let's add this here. This is more like formatting everything. Here we add the sun, so let's add it here. And what do? Well, we create a plot, x plot, and then we say we take this one, the scaled vector from the sun to the barycenter and only the xy values. And here we take only the x values. Now let's make a new line maybe. And this must look nicely. And this is the y value. And then we can say, okay, maybe line style should be solid. Solid. And let's take also a nice color. I looked that up. I like it. It's royal blue, so it will not burn in our eyes. Maybe we have to set the alpha value. I don't know. Oh no, it looks nice. And you can see here, what do we see here? We see the sun, top view, so only the X and Y plane. We see the solar system barycenter is the blue line, and how it propagates over time. Now we don't know where's the beginning, where's the ending, so it's maybe a small task for you to draw like an arrow here or something. But what you can see is that the solar system barycenter is leaving the sun, so the sun is also revolving around a common gravitational center. So you see it even goes up to 2 sun radii. So it's pretty amazing, pretty interesting if you consider how huge the sun is. And yeah, the planets, they're just scattered all around and they are far away, but the gravitational pull is strong enough to really pull the solar system barycenter out of the sun. And that's also the reason why we should consider the solar system barycenter for our computations, for our state vector and everything, and not taking the sun all the time as the center, because otherwise our orbits become, or trajectories become a little bit wobbly, let's say, based on this shape here. I know it's covering now 30 years, so within a few days or weeks, it's only moving a few kilometers maybe, but still, it's an important thing to consider. Now, maybe interesting would be to know what is the percentage of the time the solar system barycenter is outside the sun. Now we can also compute it. We use the scaled value again, and this time we call it not position but the scaled distance. So we will compute the distance, and how we do this? Well, again, lin-arc norm from the NumPy package. We use the scaled axis equals 1. Let's take a look whether this makes sense, just here, quick and dirty. Yeah, we see values, 1.6, 1.6, 0.9, yep. Okay, the length should also be 10,000. Yeah, looks also nice. Perfect. So we can get rid of this. And now we can say, okay, I want to compute the Solar System Barycenter outside. No, I don't want to dictate. Thank you. I think I'm good enough, hopefully. Solar System Barycenter outside the sun. Let's say it maybe are the delta days, not the initial delta days, but the number of days the Solar System Barycenter is outside the sun. And we say, well, it's the length of an array, and the array has to fulfill a certain condition. And the condition is that the scaled distances have to be larger than 1. Now let's see. What's the result? 1. Okay, maybe I did something wrong here. Let's take a look. Ah, not the length. Okay, it's the first entry. Okay, so it's 0. That should work, I think. Now the length of this one. Object. This is strange. What's the problem here? Let's take a look. Ah, it's already the length, yeah. Ah, and you see the length of the vector is 6,464. Now, if you recall, the delta days we computed were 10,000. So around 60, so it's like 65% of the time between 2000 and 2030 or 27, the Solar System Barycenter is outside the sun. And I think this is pretty amazing. Again, if you consider how small the planets are compared to the sun. Well, what are the gravitational, or what are the main drivers of this? Well, I mean, this appears to be like a trivial question. It is a little bit, but next time we will have a look at this and also create some plots to see what kind of influence Jupiter has and Saturn, not from a, let's say, gravitational theoretical perspective, but more really from a analytical perspective. Until then, I hope you enjoyed this. I hope you enjoyed the tutorial, and yeah, you can play around with the repository. The link is in the description. And see you next time. Take care.